Again, something about electrical energy, but right now I will focus more on microgrids, how to control the microgrids, how to guarantee the stability of the microgrids, and what can they provide. I will start with the let's say definition of the microgrid. It's a local electrical grid that acts as a single and controllable entity. And a special kind of microgrid is a DC microgrid, which is the grid that has the DC voltage on the common bus bar. The thing is that if the company has some photovoltaic panels on the roof, the output of the photovoltaic panels is DC. The input needed for the machines is typically also DC. Then it makes sense to get rid of the AC part, AC-DC and DC-AC conversion for the microgrids, and to focus on the DC distribution. This idea is relatively, I can see, old, maybe more than 10 years. But in the past, it was relatively costly to have all the electronics, all the circuit breakers and other components that are more difficult and costly for the DC microgrid. But right now, the prices and also the availability of the components, cables, circuit breakers are getting more available and cheaper compared to the AC components. So it makes more and more sense to think about this kind of local distribution. I will talk about the project or the cooperation that we are doing with the company Eaton that has the laboratory in Roztoky u Prahy, Czech Republic. And in this laboratory, there is the equipment like the batteries, chargers for the electric vehicles, controllable and uncontrollable loads, controllable sources, active front end that is connecting the DC part with the AC part, and all those power components. And we are investigating the algorithms, how to control the microgrid, how to provide the optimality of the operation. It means how to decide when should we start charging the battery, when should we use the electricity from the battery, when should we use the battery from the AC grid through the active front end, and how to optimally control this system. Maybe I should emphasize that here we are not considering right now the islanded mode. We expect that the microgrid is connected to the AC grid and can get the electricity from the AC grid. As I mentioned already, dynamic simulation is a significant part of our work, and we started with the modeling and simulation of this system. Here it is not only for the sake of testing the performance, but also to formalize the constraints and provide a support for the optimizer, because we are using some version of the model predictive control MPC, in fact the rolling horizon that is considering how the system will behave in the future, but we are applying the first step only for the control, and for all those stuff, model and simulation is an important part. Here you can see the formulation or simplified formulation of the optimal control task. The goal is to find the vector of power. The power can be plus or minus, meaning charging, discharging the battery, and the power for the central battery, for charging the EVs that are considered to be in the garage and that should be charged, and as the cost function for finding the optimality is mainly the price of energy from the AC grid that is needed. So the goal is to find such power balance that we are maximally efficiently using the cheap energy from the local photovoltaic panels sources to utilize the battery for peak shaving and for smoothing the energy demand from the AC grid, and to utilize the such energy from the grid that is in the low tariff, and try to avoid the peak tariff. Plus, of course, we have to consider the constraints of the battery state of charge that has some maximal value, some minimal value. It can be from, in the theoretic case, from 0 to 1, but from the practical point of view, it makes sense to restrict the state of charge to, for example, 30% of the battery capacity as the minimum and 90% as the maximum, for example, but it depends on the battery vendor and battery parameters. And as well, there are some limits for the energy exchange between the DC microgrid and AC distribution grid. Therefore, there are some limits of the energy that can be transferred through the active front end technically, because it has some nominal power, but also some distribution limits for 15 minutes and other constraints. Important part of this research and of this approach is the flexibility and modularity of the solution. Because one of the features of the microgrid is that we have to consider all components and calculate, control all components, and to guarantee that the control as a whole is stable. This is not like from the customer point of view, this is not the case when we are using the public AC distribution grid, because the stability, guaranteeing the stability is the goal for the transmission system operator, TSO. But here in the microgrid, the users, all the components that are connected to the grid have to consider the available energy and adjust the consumption according to the energy situation on the grid or in the microgrid. We've designed a simulation model in MATLAB Simulink that models the most important parts of the grid. Here I would like to emphasize that it can seem that we have two blocks for the majority of the components, but it's there are some differences. So, for example, here between the converters, we are distinguishing between setting up the power that should be transferred through the converter, but also the so-called virtual impedance that is some kind of virtual virtual number that can be considered as some kind of resistivity on the input side, specifying that if there is not enough energy in the grid, the consumption or the production is adjusted according to the virtual impedance. So in the DC microgrid, or one way of control of DC microgrid is to use the so-called droop control. And droop control means that we are not using the set point of the voltage in the grid, for example 700 volts, but we are modifying the voltage in the grid according to the production and consumption in the grid, and the components react on the voltage in the grid by considering their consumption. So, for example, the battery charger supervises that the voltage is in the grid is lower. It's, I don't know, 695 volts. Therefore, it means that there is less voltage than is lower voltage than is the nominal value 700, and it means that it should accordingly react on the charging and discharging in a way that there is no enough energy in the DC microgrid at that point in time. So this kind of droop control, considering the voltage and considering some kind of virtual impedance, virtual resistance, can react on the situation in the microgrid in a way that it's just measuring the voltage, but it doesn't require the fast informatic feedback or informatic control by a different channel that then is just the power cables or the voltage in the common bus bar. But of course, the output of the optimality or this kind of behavior has to be set up, and these droop curves, these virtual impedances have to be adjusted according to the output of the optimizer, because if we want to store the energy in the battery, then the slope of the droop curve of the virtual impedance is different than if we want to use the energy from the battery, for example. So these are just details to the library in MATLAB Simulink, and here we can see the model of some basic microgrid that we utilized in the laboratory, and here we can see some kind of example of simulated results. With these surfaces, we can see the shortage of the energy production coming from the photovoltaic panels compared to the uncontrollable load, and surplus of the energy, expressing that we have enough energy. On this figure in the bottom, we can see the state of charge of the central battery. I mentioned the maximum and minimum state of charge constraints. So we are considered 90% of the capacity as the maximal state of charge of the battery, and here I think it's 20% as the minimal state of charge, and we can see how the current state of charge evolves in this simulation and optimization period. And in the figure in the middle, we can see the state of charges of 5 connected electric vehicles. And here, just to explain the numbers, each vehicle is in the range 0 to 1, but I shifted this to this range just to be able to read the figure. But in all lanes here, it's just the range from 0 to 1. As I mentioned, very important part of this microgrid control is the reconfigurability, flexibility, modularity, because if we modify, for example, the battery, we add some new modules for the battery, we have to change the optimization task, and we have to set up that the task task to be solved is different after this change, and it's very important to do this in a modular way. Of course, very straightforward part is that, for example, some of those 5 electrical vehicles is no longer in the garage because somebody leaves the house, and then it means that we have to change or we have to automatically change the model that is optimized, and consider the new situation, in some sense new topology of the system. And this kind of flexibility and reconfigurability has to be built in the simulation model, in the model of the system itself, but also in the model of constraints and of the formal model of the building that is used for the optimization task. Another important part is also the flexibility in the integration part of the model, because the optimizer, the simulation model that is used for the testing, validate new optimal setup, and the real machines have to be integrated and synchronized properly. Therefore, the devices have to be integrated in a flexible, reconfigurable manner. As I mentioned, the situation, for example, in the garage is evolving from very frequently. Cars are coming in and going out. State of charge of the car can be significantly different than is expected in the model. Therefore, the models have to react on all those changes, and therefore we are using, for example, the generation of the model to consider the current number of cars in the garage, and model the cars to estimate what could be the state of charge when the car is coming again, to detect differences in between our predictions and the reality, and yeah. So let me conclude. This presentation was about the prototypal implementation of the DC microgrid that is being tested in the Eaton laboratory. We've designed the simulation-based test environment for stability testing and tuning all the optimization algorithm. We've designed the optimization algorithms using the MILP and PSO meta-heuristic, and we can also support the model-driven techniques for modifying the simulation and generating it for the actual situation. Thank you all for your attention.